All right, welcome to today's notes on average rate of change. To get us started, I've got three warm-up problems to review concepts that we learned in the past. Go ahead and pause the video here and take a moment to execute on those problems. Okay, so the first problem, if we were to solve this for x, we can subtract the 5 and that gives us 14, and then divide the 2, and that gives us 7, and then by taking the log, or the natural log of both sides, that brings the exponent down in front, and then finally if we solve this for x, we would arrive at the answer ln of 7 divided by ln of 3. The second problem is asking us to draw a sketch, so this is a transformation of the quadratic function. Getting some white balance issues going on. When we take this quadratic and we shift it right to up 1 and flip, we get a quadratic, right 2, up 1, and then the quadratic has been flipped so it opens in a downward fashion. Okay. And finally, the last two problems are evaluating trig expressions. 5 pi thirds is located in the fourth quadrant, and sine is looking for the y value of that. So we notice that it is a negative one because sine is in the fourth quadrant, and the y value at that location is root 3 over 2. Tangent of 7 pi 6. If we think about the unit circle, 7 pi 6 is located in the third quadrant, and tangent is the sine value divided by the cosine value. Those two negatives cancel, and the divide by 2's cancel, and we get 1 over root 3, which if we rationalize that out is root 3 over 3. All right. Moving on, our learning objective is to interpret the rate of change at an instant in terms of average rates of change over intervals containing that instant. So we're going to be focusing on how to find average rate of change in this video. I've provided a graph here, and I'm asking you to ponder, when we look at this curve, how do we find the slope at specific locations of the curve? In the past, we've dealt with slope of straight lines, and as we move into the world of calculus, we're moving towards finding the slope of curves, or the slope at a specific moment of a curve. So I want you to ponder that and see if you can come up with a way to calculate the slope at a specific point, or at least think about a possible way. All right. If you remember, calculating slope is a matter of counting squares, is how some people refer to it, where we're counting how many squares did we rise versus how many squares did we run. And if you were to do that, for example, on this line, which is touching at point A, we rose 0 squares and we ran for several squares. So rise 0 over a run of, in this case, 3 would give us the slope at point A is 0 over 3, or 0. Okay. So as you can see, what I did is I came up with 2 points on the curve and calculated that rise over run. I'll put that over here. Picking 2 points on the line and using the slope formula. Now the slope formula is more formal than the statement rise over run, but if we were to grab, say, this point and this point on the curve, or on the straight line, we would see that we've risen 1, 2, 3, 4, 5, 6 squares for a run of 1 square. So the slope at point B is somewhere around rise 6, run 1. So slope of about 6. And in calculus, we're going to actually find ways to find the exact value here rather than this process of counting squares. So slope formula, for those who don't remember, the way we can find the slope is if you're given 2 points, We can calculate slope as the difference quotient, y2 minus y1 over x2 minus x1. Okay, so that's the slope formula. I've used the expression difference quotient to refer to that. Difference quotient. And you'll see me use that term throughout the remainder of the year. We're looking at differences in a quotient form. So let's practice at the most basic level, slope between 2 points. In this case, we can see our x1 and our y1, x1, y1, x2, y2. So if we were to label those out, our y2 is 1, our y1 is 2, our x2 is 4, and our x1 is -3. And so when we calculate our slope using that slope formula of y2 minus y1 over x2 minus x1, we wind up arriving at y2 minus y1 over x2 minus x1, which is -1/7. So that's our slope between those 2 points. Sometimes you'll see teachers refer to this as the change in y over the change in x. And this is where the term, where we also get the idea of rise over run. So those are all synonymous with one another. Change in y is your rise, and change in x is your run. And as we dive into calculus, this delta y over delta x will get used a little bit more, and we'll do exciting things with it. Okay. Example 2. Given this curve, find the slope between the points where x is 2 and x is 3. So they've given us the x-coordinate. So if x is 2, we can find out what the y-coordinate is. We could say, well then, y is 2 squared plus 5 times 2, which equals 14. Similarly, we can do this for if x is 3. If x is 3, then y is 3 squared plus 5 times 3, which is 9, plus 15, which is 24. So now we have our x2, our x1, our y2, and our y1. So we can calculate the slope. Slope is y2 minus y1 over x2 minus x1. Which is 10. This is our slope. Now graphically what's going on is I have some curve, this quadratic as it is, and we're looking at the point when x is 2, the height of the curve was 14, and when x was 3, the height of the curve was 24. Okay? And when we're calculating the slope between those 2 points, what we're doing is calculating average rate of change. So slope is very closely related to average rate of change. We're calculating the slope between 2 points, or you could say we're calculating the average rate of change on a curve from one x-coordinate to another x-coordinate. So this difference quotient is going to come back to us on the next page. As we look at the next page, we see the slope formula and the average rate of change formula and how closely they're related. The difference that exists is instead of writing y sub 2, we're evaluating a function at the point. So this is like saying f of 3 in that example. And y1 was f of 2 in the last example. So in the last example, we went from 2 to 3, so we did f of 3 minus f of 2 over 3 minus 2. And this is the formula that we're going to wind up building the foundation of calculus on. This and a concept to be learned over the next several videos. So let's look at our first example, which is asking us to calculate the average rate of change over the interval -1 to 2. So I find it useful to identify all of the things that I need. So A is where I started, -1. B is where I'm finishing. And then I'm going to need to evaluate where the function's height is at those 2 points. So I need to evaluate f of A and f of B, or in this case, f of -1 and f of 2. So f of -1, we plug -1 into the equation, and we wind up getting an answer of 0. And f of 2, we plug 2 into the equation, and we wind up getting an answer of -3. So now I have the numbers for my numerator and the numbers for the denominator, so I can calculate the average rate of change. Using the difference quotient, f of b minus f of a over b minus a. So in our case, we have f of b is -3, f of a is 0, b is 2, and a is -1. Which gives us a value of -3/3 or -1. Okay? So in this curve, our average slope is 1. Sure, the slope varies because it's a curve, but on this interval, the average slope is 1. Okay? Example number 4, same approach. We identify our A value and our B value. In this case, we're going from -2 to 3. We're going to evaluate the function at those 2 locations, f of -2 and f of 3. So if I plug -2 into the expression, I have 5 times -2 plus 1, which is -5. And if I evaluate it at 3, I have 5 times 3 plus 1, which is 20. So now I have the 4 numbers needed for my difference quotient. Average rate of change is the difference quotient. F of b is 20, f of a is -5, and then b is 3, and a is -2, which gives us a value of 25/5, or 5. And this should make sense, that answer. This answer makes sense. This makes sense. Pause a moment and see if you can think why that answer makes sense. This makes sense because our original function was a straight line. And our straight line was a function, it was a shifted left 1 and has a vertical stretch of 5. So roughly something that looks like that. And everywhere on that curve, the slope is exactly the same. So our average rate of change should be the same as the slope of the line. And it does. Or it is. Okay, moving on to example 5. Find the average rate of change on the interval 0 to 2 pi. Well, if we identify our a value as 0 and our b value as 2 pi, then evaluating the function at 0 is a matter of recalling on the unit circle what cosine of 0 is, which is 1, and what cosine of 2 pi is. And if you recall, the unit circle 0 and 2 pi occur at the same location, so it also has a value of 1. So when we set up our average rate of change quotients, a difference quotient, we have this one subtract this one over 2 pi minus 0, which gives us a value of 0 over 2 pi, or a average rate of change of 0. And again, it's always good practice to do a sanity check. If we think about what this graph looks like, being experts in parent functions and their transformations, the cosine curve starts high, drops low, goes back up high again, and then this process repeats again. But at 0 and at 2 pi, we hit the maximum of the curve, or the two local maximums, and they're both at the exact same height of 1, so the average slope between those 2 points is 0. So if we were to draw that line, the slope would be 0. If we were to calculate the average rate of change, that value is 0, because slope and average rate of change are so heavily tied to one another. We could try a graphical approach with the next function, ln of x. If we would try a graphical approach to this one, we know ln of x looks something like a logarithm, and the coordinate 1 is right where it crosses the axis, and e to the 5th is a pretty large number, e to the 5th. And I can't quite tell what the slope is between those 2 points. Because I cannot tell the slope exactly off of the drawing, I'm going to actually use the formula, and in fact, we should always use the formula when calculating average rate of change. Drawings just help us confirm whether or not we have something that sounds reasonable. So this drawing tells me I should get a positive number because the average rate of change, the average slope looks positive, and it's a pretty shallow gradient, so I'm imagining a number that is probably less than 1. But let's execute. A equals 1, b is e to the 5th. So when I calculate f of 1, I'm asking what is ln of 1, which I know to be 0. Log base anything of 1 is always 0. And if I need to evaluate f of e to the 5th, that'd be ln of e to the 5th. And log properties tell us that natural log base e, those will cancel each other out. And so ln cancels the e, and we arrive at an answer of 5. So when I set up the average rate of change difference quotient, I will have f of b minus f of a over b minus a. And this gives me a value of 5 over e to the 5th subtract 1. This is the exact answer. And if I wanted to find a decimal approximation, I would want to turn to a calculator to type that into a calculator. Five divided by, there's multiple terms in the denominator, so I'm going to go ahead and put my denominator in parentheses. Second, e to the 5th, subtract 1. And I get a decimal of approximately 0.0339. 0.033. If we truncate that, if we were doing rounding, 0.034 would be the rounding answer. Alright, now let's wrap up this video with example number 7. In this case, we don't have a function rule. What we have is a table of values. So the rule is hidden from us. However, we do know how to evaluate the function. For example, f of 1 is 10, or in this case, since our function is named y, we would say y of 1 equals 10, y of 2 equals 17. And so when we're setting up our a, b, and our f of a and f of b, we have a is 1, b is 5, y of 1 and y of 5 would be the two expressions that we need to evaluate, and we use the table to evaluate those. So y of 1 is 10, and y of 5 is also 10. Then we set up the average rate of change difference quotient. So the y height at point B minus the y height at point A over point B minus point A. And this gives us an average rate of change of 0. Okay. If we wanted to attach units to this, perhaps the height was being measured in meters. It doesn't say it, but we'll add that in there. Meters. So the average rate of change was measured in meters per second. Okay. So we have this particle that's moving up and down on the y-axis. So it moved up and then back down. Looks like it went up and then down and then back up and then back down. And probably there could be some other behavior in each of these intervals, but in general, that was the movement. So in general, the average rate of change from time 1 to 5 was 0 meters per second. That is not to say that the particle did not move, because we see clearly that it did move. It just had some upwards movement and downward movement. Part B, we take the same approach, A of 1 and B of 3. So we're going to, in this case, evaluate y of 1 and y of 3. Consulting the table, y of 1 is still 10. Y of 3 is -5. So it looks like over that time it dropped in height. So we should get an answer that is negative. If we do our average rate of change, -5 subtract 10 over 3 minus 1. Gives us -15 halves, or -7.5. And if we're assigning units to it, our y values are being measured in meters, and our x values are being measured, or our t values are being measured in seconds. So on average, it dropped 7.5 meters per second. Now recall that this is on average, because we see it went up and then it went down. So it has both movements, but on average it was moving downward over those 2 seconds. Finally, for the last one, we're looking at the interval from time 1 to time 2. So A is 1, B is 2. Y of 1 is 10, and Y of 2 is 17. So we can see over the 1 second it went up 7 units, so we should get a positive average rate of change because it was generally going upward. If we write this out, we get 17 minus 10 over 2 minus 1, which is 7/1, which is a average rate of change of 7, and again the units in this case were meters per second. Thanks for watching. Be sure to mash that like button, comment, subscribe, throw some change into my Bitcoin wallet, etc., etc. I'll cover the further examples in the next video. Have a good day.